Hi, I'm Jeremy, and this is my colleague here, Jack. We are here to talk about exploring the new state tree for AI. This is a really, really new tool, and to be honest, just a bit of an expectation check. We are here to kind of show you all getting into state tree and why we use state tree. What are some of the common challenges that it solves? So I'm really curious. Can I see a show of hands who has tried state tree? Wow, there's a lot of them. Okay, nothing we show you here is going to be groundbreaking, but I think this is more like a bit of a discussion on the previous AI model that we built on behavior tree and why we go to state tree and what problems it solves. I'll jump straight into it. Who we are MLBlock Studios. We are a games development company based in Malaysia. We are about 50 developers. We build IP and do co-dev projects as well, mostly for PC console, occasionally mobile. We do mostly multiplayer session-based games. So we worked on Eximius is the frontline. Me and myself as a technical director, and Jack does a lot of the gameplay elements. We both do some parts of the AI. So most of our projects are multiplayer session-based. We also have a few other new titles in the pipeline. So we also do work for hire staff, code development staff, and also prototype mechanics development. So most of our work are primarily Unreal Engine stuff, right? So what we'll talk about today is first behavior tree, how we build our AI in behavior tree, and what are the challenges, and then we'll talk about why we use state tree, and Jack will do a little bit of a live demo, how do you get started into state tree, what are some of the tips and tricks, and then a bit of a live demo, kind of a show and tell on the completed project. So how we use behavior tree. So first things first, you must be wondering what's wrong with behavior tree, right? Why are state trees needed? Behavior tree is technically a more modern solution compared to the finite state machines because it's built to sort of avoid the messy graph of finite state machine that gets really, really, really big, right? So before we explore why we use state tree, let's look at our AI needs. So I'm going to show our flagship title, Eximius, that we built a couple of years ago, and why behavior tree is problematic, right? So a bit about the game. So Eximius is a 5 versus 5 shooter game where one player opts to be a commander. So you build units, and then basically commander does RTS stuff, support the players on the ground. The rest of the players, battle on the front line. So being an FPS in an RTS world, it involves a lot of AI entities. You have infantries, you have vehicles. The units can fight individually. They can also fight as a squad. So they can be given direct orders, as you can see. Or they also can be given kind of high-level orders to follow the players, and they will take cover as they move and shoot. And then if the situation, they have enough confidence, they will move forward. So it has sort of layers of logic. And what makes it really complicated was that the layers of logic needs to interrupt each other, right? You give them a high-level order, but the low-level order could interrupt the high-level order, and vice versa. Okay, let's move on to how we actually build them, right? So what we needed, so a little breakdown, a recap. We needed an AI that's very, very performant because we need about 100 plus AI entities. And we kind of benchmark it we decided we need at least 50 infantry per team. So we kind of put a population cap so it doesn't go more than that. And because we cannot use 100% RTS AI, they need to be they need to have raycast, they need to have vision. Players need to be able to hide from them. So you need to have real FPS level kind of AI. So we needed a lot of entities, so they need to be performant. There's also multiple class, so there needs to be vehicle, there needs to be grunts, and there needs to be bots. So bots basically means AI that replaces humans. So when there's not enough players, we get the officer will be played by bots. And we also needed the commander AI, right? So there will be one AI that will be building the structures and supporting the players on the ground as well. So we needed multiple classes, and we also needed AI that has individual and group behavior, as we mentioned just now. Means they will be able to fight singularly as a unit, but placed in a group, they would kind of behave slightly different, but they still need to be shoot as if they are individual. And they will have low-level combat goals, I'm trying to get it alive, I get shot, I'm taking cover. That's low level, right? And they also need high level, as in I'm taking cover, I'm shooting, but I'm moving towards there. So that's a high and low level part. So that's what we need. So here's where our trouble begin, right? So having to build our AI in behavior tree, which, we started building this in full production in 2017. So generally, the de facto solution is behavior trees, right? So, but obviously, understanding that building AI behavior tree is not the only components. There are other things like EQS, the controllers are part of it. But the main logic sequences, well, we ended up using behavior tree, right? So let's look at them. So problem number one is that, problem number one with behavior tree is that they are very bad at states. So we understand you don't want to put states in behavior tree because they are not state machines. But the reality is that a lot of video games AI ended up having states, am I right? Like you're going to have like aggro, non-aggro states. So you ended up building trees with like aggro, non-aggro, correct? So you'll have states like, am I idle? Am I panic state? So a lot of NPC AI tend to have a lot of states. So this is a very typical bot-like behavior. Again, highly simplified. It's not an exact tree. So we have like you plan for the goal, right? And then you execute the goal. So during the planning of the goal, you will say, oh, if I'm idle, I will look for the goals here, right? If I'm fighting, I'm in combat, my goals are different, right? And then I execute a bunch of linear tasks, and then I do a bit of wait. So this is very common, right? So whenever you want to add a state to it, the problem happens is that, so for example, you want to add a cover. So you're going to have to do this. Suddenly you will have, you have to find a goal for cover, and then you have to make like, oh, if it's not cover, you have to do this, because suddenly the covers will now affect all this, correct? So if you have like a state that cuts across vertically in all the logic, so it starts to get complex. So, this is a very simplified problem, but if you have built behavior trees before, you will know that it quickly gets very big. And the other problem is that it's not just adding, removing as well. If you're trying to remove a particular behavior, you have to start to go into like, oh yeah, but this doesn't work anymore. I have to change the way it works. So that's problem number one, right? And it gets exponentially more complex with more permutations, and because a lot of AI requires states, you will end up having to do it. Okay, the second problem, transitional logic. So behavior trees are not very good with transitional logic because it's very hard to describe exactly where you get exit from. So if you look at selectors, right, you have selectors and selectors within selectors, and the observer at the top there could terminate anytime, right? So observers are basically, decorators. So decorators are observers. So at any time, the decorator could fail, and it's a bit hard to expect where it's going to fail from, correct? So if you want a certain logic that says, if you're failing from task 3, I need you to do this. If you're failing from task 1, I need you to do something else. It gets problematic, right? So our option is to code the logic in the task itself. Like task 1 would have on task fail, you do something else before you exit, right? So that seems to be the one of the common solutions. Like another common example is that if you stun a character, right? You want to stop the guy, but it's very hard to say, okay, now that you are stunned, I want you to do something else. I want you to transition to this, and that. So the only way behavior tree does that is that you have to terminate it and then force it to rerun again. So it's not really good in transiting, and it becomes one of the problems. So of course, this problem doesn't affect all kinds of AI. We find that like AI that thinks for itself, generally very autonomous AI that you don't tell them what to do, they try to think, they find the best solution, works very well with behavior tree. But if you want AI that relies on sequence of event or like scripted behaviors, I call it like a cyclic behaviors, like it tends to do this and this and this, and anytime you knock them into this, it does these things. It's just not very, this doesn't work very well with behavior tree, right? So problem number 3 is that they don't work well with multiple responsibilities, right? When you're trying to build multiple track of responsibilities, like when they interrupt each other, they tend to be problems. So you start running the logic and then you are out of ammo, you need to do something else, you need to think of, hey, weapon systems, do I change weapon? Do I fight a new target? Now I'm given a new order. So when you have multiple responsibilities, then you start to get into complex problem as well, because you cannot divide and conquer. Like this bunch of states do this bunch of states do that, right? So, I've spent like the last 5 minutes trash talking behavior tree, right? So, but really, don't get me wrong. It's like there are certain things that just works well with it, but these are the things that doesn't work well with it. So, modular behavior also doesn't work very well. Okay, so I'll go straight into how we did it in Eximius. So to have all that bunch of logic that I said just now squeezed into the behavior tree, so we ended up doing this, right? So the combat logic is handled in trees, so where we do low-level combat sequences. I'm getting shot at, I'm taking cover movements, the different, like I'm reloading, I'm shooting. So these are all low-level combat logics we put in behavior tree. So we ended up still having to do states. So we do a lot of states in the controller. So we manually squeeze our aggro states, the weapon states, and the targeting states, and they would then push different sets of data into the behavior tree and does like really fancy stuff. It gets really messy. We also needed extra system for like high-level goals, RTS commands that says, oh, now you're in repair. I'm going to lock the behavior tree until the repair is done. So this is how we ended up doing it, and this is the part where we wished we have state tree, right? So there are other smaller limitations like execution costs, because behavior trees have to, whenever something fails, you have to run the whole thing again, right, to get to where you are. So there's a lot of execution costs, decorators, parallel tasks is a problem as well, latent tasks as well. So I don't want to go too deep into it. I will go straight to state trees. So what is state tree? So state tree solves a lot of those problems that it presents. So first of all, state tree is not a finite state machine. We are not devolving into finite state machines, right? So state trees is basically a hierarchical state machines. Basically, it's a mix of selectors and state machine, like a behavior tree style selectors. You get the benefit of FSM. FSM is a finite state machine without the downside of a messy graph. So how does it work? It's a form of FSM, but it allows states within states. So you have a container states, and you have multiple states in that containers. And the container itself can have several logics and rules, and so the states normally would have their own rules as well. So hierarchical state machine offers a solutions by grouping this, and the task can be hierarchical itself. So let me give you a visual example, right? So a regular finite state machine looks like this. Like anim graph, you guys done animation graph before, right? So in the old Unreal Engine 4 animation graph, finite state machines, they all look like this, but as it gets bigger, it gets messy, right? So hierarchical state machine helps you to groups into them, and it allows for hierarchy as well. So when one part of the logic runs, it only needs to think of the transition to the other parts if it's connected. But then the group itself can also transition to another group, and then only the states there are then considered. So this allows us to divide and conquer certain behaviors, like you only need to consider this bunch of behaviors. And this becomes very, very effective, like bringing a group together in a hierarchical fashion. So why use state tree? So one of the interesting additional point is that it's flexibility. So state trees is very flexible. It can be used for AI behaviors, and it can use for non-AI behaviors. So later on, Jack will be showing you all how we can actually use state trees to do even non-AI stuff. So you could build arbitrary state machines in actors, and you can even do it on UI, right? You can have those fancy. How many of you have actually coded state machines in widget blueprint before? Right? You would have like, zoom, the UI would come out and then it's ready, then it transition out, right? So you can even do that, right? So you can do state machines in a lot of different things that's non-AI. So behavior tree, as you know, is tied to AI controller. It just doesn't work without AI controller. It's not the case in state tree. So it's easier and cleaner to handle complex AI with multiple states. And the third one is that the binding data allows you to be very organized. So it allows data binding, which is like a lot like how widget blueprint binds the data, but later on he will show you. So it's easier to bind data without getter and setter. So the blackboard in behavior tree has all these arbitrary data types that you have to set as something, get as something. So state tree avoids all of those problems. So yeah. So how to use state tree? I will pass to Jack. So he's going to do a bit of a demonstration.
All right, good afternoon, guys. So right now, I will show you an example, a demo of the enemy AI that will constantly chasing you and will attack you once he's reached the player. Yeah, it's just a demo. Yeah. All right, so how do you start with a state tree? So for those who don't know, I will just quickly go through it. So you just need to enable them inside the plugins, search for state tree, enable gameplay state tree, and state tree. Yeah, these two, and then you are good to go. Next, so you can add the state tree component inside the actor you want to run the state tree. For example, in my case, I want to put my state tree inside my AI controller. You can put anywhere else too. And then right here, inside here, then you put your state tree, the state tree class that you want to run in. If you want the logic run automatically on begin play, you just need to tick this. But if you want to activate it manually, you just need to call start logic. Yeah, all right. So let's go into, so this is the view of the state tree. So on the top left right here, you can see there's a context actor class. So this is the actor class that you are supposedly to run this state tree on. So in my case, I put my AI controller. But you can also put a base actor class if you want to, but the higher the class, the higher level of the class you put in, you get more data from the context actor. All right, so the schema. The schema is the class of the safety component. So in 5.4, there's this new state tree AI component. This is the guarantee that there's access to the AI controller. So your context will be 100% AI controller. But for in my demo, I will use the base class. Oh, it resets. Yeah. All right. So let's go to. So this blue node is a state. So each state has a name, the color, the type. So there's also different types of states. So let's look at this has target state. So this state is a group. So a group type of state is a state just containing the child states. You can see right here, and it doesn't run any tasks. So at normal state, it has a category of tasks. So you can run any task inside it. But if it's a group state, it just containing child state. It's just for a grouping purpose to make it more cleaner. All right. So besides that, there's a state which is the normal state, with containing tasks and child state, and then there's this link asset and subtree. So these three are very special. So I will go to another example. So this link asset type is also new in 5.4. So this link asset type of state allows you to connect another state tree within the current state tree. So for example, if I want to run follow player state, then I can link to the follow player state tree that I already made it, or run away from player state tree. So this allows the modularity of the state and makes the state tree looks cleaner. And next will be the link state. So link state and subtree works together. They can't work without each other. So there's a link subtree right here. So you have to connect to a subtree. So what link tree basically do is just once it goes into this state, you jump to the subtree. Yeah, that's it. You can use this to separate very distinct AI behavior or different state. All right, so next. So inside this has target state, you can see there's a question mark here. You wonder why is this? So this question mark represents enter conditions. So you can have enter condition in every state. So enter condition works like decorators in behavior tree, but they are not observers. So once you come inside, even though the enter condition fail afterwards, it won't go out from the state. Yep. So okay, another thing for the enter condition is if this state has any child state, and if none of the child state enter condition is passed, this state will also fail. So when the enter condition fails, it will go to the next sibling state, which is the target invalid for in this example. Yeah. All right. So let's look at the next state after the has target state. So inside this state, I named this check within distance. So what this do is this state has a task called check within distance. So I use this to check the distance to the player. So this is the loop inside this task. So each task has a few functions. It has enter state, exit state, state completed, and tick. So it's pretty straightforward. So you run enter state once this state is entered, and exit, and state completed, and tick. Yeah, it's pretty straightforward. All right, so there is one. So how do you exit the state? So you can exit the state with a few ways. So one is called finish task. You can either make it the state succeed or fail, depends on your conditions. And then later on, you can use this condition to trigger another transition. Okay, so beside this, I will show you later on different ways of transitions. This is just one of it, a very basic one. So there's another special thing inside the state tree is, so you can see right here, you can see there's a point variable with a in icon here and target in input here. So once you give the variable of a category of input, you can later on bind the data within the state, just like this, just bind. So for example, I want this point to be my currently control point, and the target I want to get from my actor. So actor is the context of this state tree. I wish I can rename this. This is very confusing. So actor and target actor. Yeah. So beside input, you can also have output. So for example, I have this output category, height difference. So you can output a float, and then you can use this float to use it anywhere in the state tree later on. So for example, I have this, maybe I have a distance compare, and then I can just bind this to the chase player height difference. Yeah, so you output here right here. So there's one new thing in 5.4 as well. There's a lot of updates because this state tree is still typically new, so it still gets a lot of updates. So there is these parameters under each state. So you can bind, for example, I make it test boolean. So this parameters is visible to every state within the hierarchy. So for example, inside my chase player, I have this delay task, and then I can bind this to the test boolean right away. So you can have different parameters within the state. Right. So besides output, we have also context. So a context category is very straightforward as well. So we automatically bind to the context actor of this state tree. That's it. So I have this AI controller. So we bind to the actor, which is my context actor. Again, I wish I can rename this. Yeah. So what are the ways to capture the data to pass in to use it within the state tree? So we have this thing called evaluators right here. So evaluators provides a way to expose the data to the state tree that can be bound anywhere in the state tree with an input category. And then the evaluators are a separate class that can be executed in a state tree during runtime. So I will show you the example of the evaluators. So I have this STE point data. So inside the point data the evaluators is similar to a task. It has a 3-start, tick, and 3-stop. So it will run 3-start when this state tree is activated. Yeah, so there's 3-start. I will output. So you can see right here, output. I will output my current control point, and then I'm able to use it if anywhere in the state tree. I can just bind to it. So evaluators, STE point data, control point. Yeah, I can just straight away bind to it. So it's more cleaner than the blackboards. You have to set, and then you get value, and then get value as boolean. Yeah, it's a lot of works. So okay, all right. Next, inside the state, you can see right here there's a selection behavior. So selection behavior is part of a major feature in the state tree. So the try select children in order is a common one. So what this do is, if this state has a selection behavior or try select children in order, so he will try to check if this state has any child state. For example, has target state, has a child state, yes, then he will go right down here. If this state has any child state, and with this selection behavior, yes, then he will go right here. So this state will currently start running. Also, every task in the state you run concurrently, so it allows a parallel execution. So for right here, you can see tasks. You can add multiple tasks, anything you want. And if one of the tasks completed, succeed, or either fail, it will trigger the transition. So it will jump out from the current state. Depends on the transition. So for example, if this parent state has a task and a child state has a task as well, so both tasks will run at the same time too. So we can see, let's see in the visual way how this selection is working. So in state 3, there's a debugger as well, visual debugger, that allows you to debug. So we can either put a break on enter, or we can put a break on exit. So let's see how it goes. Oh no. All right. Okay, see. So you can see right here it breaks, and then you can see the column that is already highlighted in yellow. So it shows where the current state is running in, and then you can, yeah, case. All right, it doesn't work correctly. All right, so there's this bug. So sometimes the breakpoint doesn't break, and sometimes it shows the wrong state. But what you need to do is just restart it. So let me start it. And then if you don't see a debugger right here, go to the window and then debugger. Okay. Yep, now it works correctly. Yeah. All right, so in this debugger, there's a few cool stuff. There's a, let me maximize it. So you can write here, it does record the previous execution. And then later on, you can even look back on the previous execution. Like, so you can debug where it's actually having issue end. Yeah, right here. And it does record for the second one if you start a new activation. So you can even reset it as well. Yeah, it's really cool stuff. All right, so I have talked about the, sorry. I talked about the try select children in order. So next is try enter. So try enter state is whenever this state is considered for a currently selection, it will try to stay at current state without going to the child state. So let's see how it goes. And it doesn't work. Oh, sorry, I forgot to compile. Yep. Yeah, right now, so he will state the current check within distant state. And he's standing there because he's not running the chase player. And once I go near, then he will transition to the active state. Yeah, so it depends on the situation or the transition you want your AI on to run. So there's another last one called try, oh sorry. So none is basically none, so this state cannot be selected. So there's one last one is called try follow transition. So try follow transition state will ignore every task. Will ignore every task within the state. Oh, sorry, I changed the wrong one. So follow transition. This one. This one will be this one. Yep. Sorry about that. Yeah. So right now you can see he's doing something. That is because it will ignore this state. It will ignore every task within the state and straight away goes to check for the transition. So the transition for this task is go to attack. So he will try to attack the invisible man, I guess. Or maybe this zombie has some drug on it. All right, so let me change back. All right. So let's go to the next state. So this is, so after I check within distance, so I run chess player as well. So the chess player has a state called, has a task called chess player, which will constantly following a players. So there's this height difference output here. I just want to demonstrate you can use output. So next one, the most important thing in stage 3 is transition. So in transition, you can have multiple transition like here, like here. So there's few trigger for the transition. So there's on state completed. On state completed means is either the state succeed or fail, either. And then there is on state fail, which if the task is fail or the state is fail, then he will trigger this transition or either succeed. And tick and event. So on tick is pretty straightforward as well. So if you have on tick transition, so each transition you can have condition as well. And then you can make your own condition as well using a blueprint. So for example, I have this Boolean compare, I have this test Boolean. If this test Boolean, so for this transition, you will always check on tick. If this Boolean is false, then he will trigger the transition to the root. And then right here you can see there's a question mark. Question mark is the on tick transition. X represent the fail transition, on state fail, and then there's a succeed. So you can see a little icon here, right here, is very readable. And the last one will be event. So an event will trigger the transition once you receive a gameplay tag. So for those who don't know or never heard about gameplay tags, so gameplay tag is a predefined label that is similar to fname or enum describing a state value. So it's basically just an fname. So for example, if I have, let me show. I'll change my state 3 class. So right here, I have implemented a trigger on event. So this event will listen to a gameplay event high health. Apologize for the bad naming. A gameplay event low health and high health. So once it receives this event, it will start transition to the crawling state. If it's a high health state, it will transition to the standing state. So let's see right here in action. So if I go up here, I interact with this thing. I activated a turret that fires at the zombie. Okay, so once his health is less than 20 right now, so it will trigger and to transition to the crawling state right here. Right, so let me just heal up the zombie really quick. Listen up. Okay, so right now he's 20. Now he's full health again. Now he's down again. Now he's full health again. Yep. Yep. So you can do transition using a gameplay event. So where do I trigger this? You can trigger the stage 3 event anywhere if you have a reference to the stage 3. So you just need to call send stage 3 event. And then just make a struct and pass in the gameplay tag for the event that you're listening to. Yeah. So in my example, I have this global task that is listen to the health check always. So a global task is a task that is start running the moment the stage 3 activates. So it's just a stage 3 task blueprint base. So the moment I enter the state, I will listen to the health change. Once the health is dropped certain amount, then I'll trigger the stage 3 event with the tag. Yeah, so you can use global tasks for some event that you want to listening globally. For example, you want to listen to the time of this level to trigger the transition for the weather or the sun, moon. Yeah. All right, so this thing right here, just now I have trigger, is an actor EP capture point derived from actor class. So I'm running state tree on this actor. So inside the ST state tree, see I have a listen team ID change, and then I have another state to activate turret, deactivate turret. So this capture point, which is an actor, activates a turret that is running on the behavior tree. Yeah, so we can do something cool stuff with state tree. And you can also do AI state tree, like what Jeremy mentioned just now. You can even do your own animation blueprint, animation state within the state tree as well. Yeah, just depending on how you're using it. So the flexibility is very high. All right, so yeah, another cool features in Unreal Engine 5.4, this is also new in 5.4. You can have colors on your state. For example, I want to add this new color called red color, and then I can color this state to red state. Yeah, so it's pretty cool. I like this kind of feature, small feature. Yeah, all right. I think that's all of my side. So yeah. All right.
So just a quick showcase of a prototype boss behavior we have in our project. So we put together these prototype boss fights in actually just a couple of days. It would have taken us about maybe 1-2 weeks in behavior tree because the task is really simple. It has a typical combat boss fight, right? It has phases, sequence of actions that fires based on rule sets. It has different abilities, attack types, targeting parameters. It also supports like coming in and out of idle, like you're getting shot at. So transitions are heavily used here. Interrupts as well, like you could stun the boss, lots of states. So in the previous title, right, the idle and aggro states have to be handled in controllers. So we'll be touching like so many different classes. So this is exclusively just on state 3. I mean, obviously you have some weapon logics on gameplay, gas systems, but majority of, actually all of the behaviors are just built on state 3. So it's really, really very fast to build behaviors. Yeah. So, okay, yeah. So, as you can see as well here, over here you zoom in, this is actually the completed tree. So for me, this is much easier to read than a huge tree. Especially when you're trying to do monolithic, right? You're trying to squeeze all the behavior into one big tree. This is much easier to read. Like, this is like one group, one group, one group. I mean, in the beginning, it does seems complex, but if you can see later on, it's very readable like a book. So you have like groups, 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 and moving in and out. You can also debug the behavior clearly in a debugger. For me, it's like much easier to read, but it get a while to get used to it. But once you're used to like the icons at the side, you will know that, oh, this one fails, go here, this one fails, go here. Then you can kind of picture it, how it looks like. So yeah, that's about it. Thanks so much. If you guys have any questions, you can ask. There's a question.
Hello, thank you for that. That was really good. Is this still working? Yeah. My experience with trees going in and out. Um, hello, hello. Okay. I had a really tough time with the idea that the tasks on a state run in parallel because I was probably thinking about behavior trees, like, oh yeah, these will just all run in a row. And I guess at the time it was even kind of hard to even, like I didn't even read anything that said they were all in parallel. I had to learn that kind of the hard way. Do you have any advice or tips on like how to sort of maybe reframe thinking about how to architect these like tasks or order of events, knowing that, because like in my head I'm like, oh yeah, I want to run these things in one state, but like I guess realistically those should probably be child states, and I split them out more or anything like that. Like any sort of insight on how do you approach setting up the tree differently because of the way states work compared to the old BT style?
Hello. All right, so I have this issue with parallel state as well. So what my approach is, I have a transition on the parent state itself. For example, the demo just now I show, I have this check for health change to the different state, which is a correlating set on the parent state So once this transition is triggered, it will stop all the other states below it interrupting. So it's interrupting. Yeah. Is that what you want?
Yeah, I think so.
Yeah.
Basically, just be a bit more, or those kinds of expectations or checks, make
Yeah.
use of the parent
Yeah,
states.
so with working with state 3, you need a really new mindset or how you structure your states. It could be tough at start. Yeah, me too. I spent quite a long time to figuring out why this doesn't work, why this state doesn't transition. Yeah.
Cool, thank you.
I have something to add to that. It's one small note is that I don't believe in the problems, the solution looking for a problem. I feel that if you don't need to run parallel tasks, just try not to run parallel tasks because running parallel tasks is always a challenge because we generally don't think like that in behavior tree. You always think of one thing at a time. But parallel tasks allow granularity. Like one of the challenges of behavior tree is that we tend to either write the task really, really small and then just do it on the graph, or we tend to write the task really big and then you handle everything, right? So it's about breaking that task into 5 pieces. And then you have certain things that is like fire and forget kind of thing that you do not want to track. Then maybe one of the tasks you want to track is completion, and then the rest is just that you just fire and forget. If it happens, it happens. So it's about having to separate certain tasks that needs to be monitored, and the rest is just a fire and forget kind of task.